Okay, good afternoon, everyone. So first, I would like to thank all the organizers for inviting me to this very nice workshop and a very nice place. So, yeah, the title of my talk is Discovery of Universal Phonon Hall Effect in Crystals, and which has been mentioned by previous speakers. And I think I will learn a lot of about the chiral phonons. And since here we have so many experts on phonons, I hope we can come up some new idea to explain this universal phonon Hall, which is very puzzling to me. Yeah. Okay, these are students and postdocs in my group. Okay, so yeah, as we know, for electron motion in the magnetic field, we have this Hall effect, anomalous Hall effect, spin Hall effect, and quantum Hall effect, quantum anomalous Hall effect, and quantum spin Hall effect. So this is a Hall effect. So if we put a temperature gradient on the sample, so these quasi-particles, when you will move from the high temperature end to the low temperature end. So for those quasi-particles, one question: can there also be some thermal Hall effect? And for electrons, there should be thermal Hall effect, and this Hall effect and thermal Hall effect should satisfy this Weidmann-Franz law. And for other charge neutral quasi-particles, like magnon, spinon is magnetic stuff. And they say, okay, there maybe also should be some thermal Hall effect. And for the Majorana fermion, if the chiral edge state, yeah, maybe also the thermal Hall effect. But if you ask, can phonon have the thermal Hall effect in magnetic field? Okay, in our textbook of solid state physics, if there's no other scattering mechanism, for these trivial phonons, there should be no magnetic effect. And usually, we did a lot of thermal conductivity map. Usually, we don't think the magnetic field will have an effect on phonon thermal conductivity. That means there should be no thermal Hall effect from phonons. Okay. So I will skip this. This is our experiment setup, and previous speaker has already explained it. So actually, in early days, Professor Ong and Louis Tafel, they measure this thermal Hall conductivity for cuprates. That's for electrons. Okay. The first experiment on the thermal Hall effect on insulator is 2005. So this French group, they checked this transverse thermal signal for this compound. It's a paramagnetic insulate, and they observe this transverse signal of the phonon thermal Hall, because it's paramagnetic, so this should be phonon thermal Hall effect. But there's some following theoretical works that maybe there's some screw scattering with magnetic. This is the magnetic ions. Okay, so also it's no magnetic order. Then in 2010, Professor Tukura's group, they observed this thermal Hall effect in this ferromagnetic, insulating ferromagnetic. It's a 227 compound. So the signal comes up below this magnetic order. Okay, and they attribute the signal to the magnons, and they discuss some DM interaction stuff. Then in 2015, Professor Ong's group, they measured another 227 compound. It's a quantum spin ice, so they also observed this larger thermal Hall conductivity, and they attribute to some neutron spin excitations, and maybe some monopole, right? Because it's a quantum spin ice. We will come back to this later. And also in 2017, also Professor Tukura's group, where these multiple magnet materials, and they also attribute the phonon thermal Hall effect. Then there's a very highly debated quantization of half-integer thermal Hall effect in this ruthenium trichloride. Yeah, a lot of debate. Yeah, this you also saw this. This is Louis Tafel's group. So giant, I answer your question. Giant means the signal, the absolute magnitude is much larger than those ruthenium chloride. So Louis has a table. the absolute value is very large. Okay, so they call it a giant thermal Hall conductivity. So the first paper, it immediately related to this pseudo gap phase. But since for this cuprate compound, the single phase is very large, so you can easily cut it and put the current along the CX. So they found a similar signal. So we immediately realized it cannot be those electronic contribution in the plane. So in the title, it's the chiral phonon, because along CX. So there's more measurement on this parent compound of cuprate. And also this is the first another measurement of the non-magnetic compound. This is STO. Okay, so and interesting a group from Michigan State University. They measure this ferromagnet, the two-dimensional ferromagnet. They found that this thermal Hall signal comes up immediately below this magnetic transition. It also, at a low temperature, is also pretty high. So at a high temperature, they attributed to this topological magnon, but at low temperature, they are attributed from phonons induced by the magnon-phonon coupling at low temperature. Okay, so this planar thermal Hall, I skip it. Is also we put the field perpendicular to the plane. So it's a conventional thermal Hall effect. So they have similar temperature dependence. So the conclusion should be the mostly carried by phonons. Okay, and I will debate that there's no quantization from On's group, and also this from Lewis group, and 227. And this is another non-magnetic compound. It's black phosphorus. Also, the signal is very, very large. Okay, this is the single crystal with a pure element, only one element. Also, more cuprates. There's planar thermal Hall effect from phonon cuprate has 214 compound of the iridium, and rotated the field direction in plane. Also, this one you got some other 2D magnets. So if we put all this stuff together, so you can see there may be 20, 30 compounds. Every time you measure it, you find those thermal Hall signal, and you give some explanation. Most time, very exotic explanation. Okay, so then several years ago, in my group we set up we built this experimental setup for thermal Hall measurements. But this is our PBMS. But at the beginning, we don't have a clear idea how to resolve this puzzling stuff of all these kind of materials. We only try to measure this series of magnets to try to compare them and find some difference. Okay. Then the real motivation for our current work is 2 years ago, I attended this workshop in Phonons, Korea, so quantum mechanism and topology. I heard the talk by Dr. Uda. I'm very glad that he is also here in this workshop. So as soon as I saw this title, this chiral phonons in this class, okay, so I immediately remember the title of Louis Taif's paper, the chiral phonon in cuprates. Okay, then I asked my student, okay, let's buy some single crystal and to measure it to see if this chiral phonon will give us this thermal Hall. Okay, so this is that Nature paper. Okay, yeah. So for this class single crystal, we just bought it, and this is the thermal conductivity. So this is thermal Hall in all three field directions. Okay, this value also giant. Okay. So that's great. Okay, chiral phonons, it has this very large thermal Hall. That's very good. And also it has a planar thermal Hall. So because quartz has this planar thermal Hall, so we also measure the planar thermal Hall of STO. We also observe this signal. It's smaller than the conventional one, but it's there. So that's great. Then we tried to start, writing the paper. Then I asked the students, okay, we should have a reference compound, which there's no chiral phonons, right? And there's no sum Hall effect, okay? So then we check a list of synchroids, okay? MGO is very trivial, right? You look at from everywhere, it's very trivial. So we measure it, so there's some more conductivity, and it is a very large sum Hall, okay? So then it's very surprising, it's first surprise. So why does this trivial insulator, MGO, have phonon sum Hall? This MAO is, we measured it later to check it, to just try to measure more single crystal. Then in our first speaker, this theoretical paper, he said, okay, for ionic crystals, yes, there should be a sum Hall. But this only I think they didn't do the calculation and get the right. They cannot get the right number for to compare with the experiment. Okay, then if it's ionic crystal has this sum Hall, or can have this sum Hall, then if we measure a single crystal with only one element, that's pure elements, so then we check list immediately think about this silicon, right? So it's an intrinsic insulator, so it's very insulating at low temperature. So we measure it, and this is the sum conductivity, and this is a very giant, even is the largest one in the sum Hall. Okay, then germanium is also germanium, and this MAO we measured later just to be sure that we have more single crystals all have this signal. Okay, so then we finally realized that the phonon sum Hall effect is a universal predictor for all crystals, right? So on the shelf you have all kinds of signals. You take anyone, you measure it, you get the sum Hall effect. And the peak magnitude of the kappa X line in silicon is about 10 watts per meter per count, which is the largest in all reported crystals so far. And also, we find this universal scaling law. So if we plot this kappa xy was kappa x and fit it, it seems to follow this scaling law. Not only for our crystals, and also for this black phosphorus measured by Professor Benya, Benya's group. Okay. But yeah, this is black phosphorus, we fit it. But for other compounds, there's magnetic stuff and a lot of impurity. There's some deviation from this universal scaling law. Okay. But actually, when we get this conclusion, we at the beginning we can't believe it ourselves. How can this trivial phonon contribute to such a large sum Hall effect? Is that possible? There's some problem with our experiment. So we did a lot of check. So first we check this glass, right? It's amorphous, so it's not a single crystal. So there's no signal, right? No sum Hall signal. Okay. Then we try to reproduce other groups' results. This is copper telluride and oxide. This our map and reference 2 is from Louis Taif's group. So basically, we reproduce this result. And I'm also not, at that time, I was not very confident with our results because this sum Hall, the curve seems always follow the temperature dependent, always follow the kappa XX. So yeah, if you have some doubt, maybe because as Dr. Luchan said, you always have some, you pick up some longitudinal signal, and you need to do some asymmetry to remove those kappa XX. So then I asked students, can we find some compound which the sum Hall signal does not follow the temperature dependent of the carbon x-axis. Indeed, there's one compound that's I mentioned before. This ferromagnet. So this is thermal conductivity. So there's a hump at the magnetic transition. This is the phonon peak here. But the thermal hole, these three empty symbols from the Michigan group. Okay, so this thermal hole behavior does not follow the temperature dependent of the carbon x-axis. So we just we got the single crystals and we measured again, and we basically reproduce their results. The thing is that now we have a single sample which the carbon xy does not follow the temperature dependence of this thermal conductivity. So then I became more confident with our conclusion, and also our result also reproduce the result of this compound. Okay. So after all this check, and now we are confident that indeed we discovered this universal phonon thermal hole. So since we claim that this thermal hole effect is the universal for all crystals, then we try to look into the literature. Is there some negative report that you measure the single crystal, there's no thermal hole effect? Yeah, as I said, in this science paper from Professor On's group, they observed this larger thermal hole signal in this quantum spin ice 227, but for another non-magnetic one, is Y2 titanium 2 oxide 7. They actually observe some small signal, but we attribute the remaining non-vanishing hole signal in this compound to temperature gradient on the brass block. That's it. So they thought this is not real. Okay. Then if this is true, that's a kind of against our claim of universal phonon thermal hole in all crystals. Okay. Then, but actually, this effect from this copper block, the heat path, Louis Type's group already did checked it and exclude this effect. So we check it by, because usually measurement we just put this sample onto this copper block. Okay, but then if there is some temperature gradient from the heat sink, maybe there is some contamination. Okay, so now we choose another configuration. So we use thick silver. We just connect it to almost 1 point at this to this heat sink, and we observe similar result for these two configurations. So that means that the effect of copper block heat sink is not there's an almost no effect. Actually, we want to remeasure this single crystal, but we didn't have this single crystal. We required it, but we didn't get it. But actually, I'm not sure if Professor Thomas Lawrence's group, this measurement is stimulated by our preprint. But anyway, in last year, they rechecked this thermal hole of these three compounds, this Y2 and 2 oxide. So they measure indeed these signals are real. Okay, these non-magnetic and magnetic, they have similar thermal hole. So that means this guy indeed has thermal, so support our claim of universal thermal hole effect in all single crystals. And there was another negative result for this KTO in Professor Benniar's group when they did the measurement of STO. They find that this thermal hole signal is very small. At here is almost zero, and here is a little. So we bought the single crystal and did the measurement again. So we find that there are also the thermal hole signal. maybe only half of the STO. So that means for STO and KTO, this is also, as Dr. Luchin said, for the maybe some sample dependence. So for, yeah, I discussed with Professor Benya. Yeah, he agrees that there's some sample dependence. Okay, then finally, I actually, because all these singles, these trivial singles, you can easily buy it, and if you have a good experimental setup, you just put in a few days, you can get the result. You can easily reproduce our result. So yeah, Professor Benya's group, they actually reproduce our results on the silicon. So actually, they use a quite big sample, but I prefer very thin sample. Yeah, then you can. Anyway, so basically now we did a lot of check, and some other groups reproduce our results. So that means now we really have the universal sum Hall, Phonon sum Hall in all single crystals. So although it's very striking, but if you look back, all these measurements, seems everything is reasonable now. So that means all previous, maybe more previous sum Hall effect can be understood. So starting from intrinsic Phonon sum Hall. So no need for this exotic monopole, Marana fermion, and I'm not sure if we need this magnum, right? Because when you know that all the single crystals are unsure, you take any one measure, you get a sum Hall. Then you observe some small signal from ruthenium trichloride near the quantum critical point of the magnetic order. Then you explain it with Marana fermion. That will be, yeah, strange. Okay. And also for this planar sum Hall, so maybe simply because the phonon can couple to the magnetic field in any direction. So this seems also reasonable to me. But the final question is how to explain it. So the origin of the universal Phonon sum Hall. So because, yeah, for this high purity silicon, you cannot explain it with any of these impurity, domain, magnetic environment, right? So it must some intrinsic mechanism. But actually, Professor Nagosa did the calculation with the traditional those ideas to calculate the Barry phase of phonons and give very, very small magnitude. So our result may be 6, 7 orders larger. So then, basically, it's very, very striking. We start from this with chiral phonon, and step by step we go to this MgO, go to silicon, and finally discover this universal Phonon sum Hall, and with this scaling law. And now we hope all these previous can be understood. You start from this Phonon sum Hall, then if it's not trivial, you examine this effect from the magnetic environment and from those impurities, and basically no need for exotic excitations. Okay, but the difficulty is how this universal Phonon sum can be explained. Is there some theory of fundamental physics, maybe related to direct coupling of atom vibration to the magnetic field? Yeah, we all know this when we encounter some new phenomenon which cannot be explained by old theory, we have to re-examine this basic of our old system and suggest new method. The phonon in our textbook of solid state is very simple and no coupling to the field. But now you really need to think about how this vibration of atom, the nuclei and those electrons, how this vibration and how they can couple to this magnetic field. Okay, thank you.